Hey, so welcome back, beautiful students. And this is part 3 of the series of screencasts. So, what we did earlier on is we did a F-test and we looked at multiple groups, or that's what the lesson was about. Doing an ANOVA one-factor F-test to look at multiple groups and making an inference about the mean based on the variance. And if you accept the null hypothesis, which means that your calculated value was greater than your critical value, then it's fine, you can finish the test there. However, if your calculated F-stat was less than your critical value, you reject the null hypothesis, which says that all the groups are the same. And so you have to accept your alternate hypothesis to say that not all the groups are same. But the problem that we faced with then is, as I said earlier, when I told you why I prefer the alternate hypothesis, which simply says all groups are not the same, as opposed to saying group 1 is equal to group 2, or beg your pardon, group 1 is not equal to group 2, is not equal to group 3, is not equal to group 4, is because we really don't know which one of those groups, or however many of those groups are the same and which are actually different. So then we perform a procedure to help us to determine which are the groups that are significantly different to the other groups. And there's a couple of procedures that we can actually perform. The one that we're going to use is the Tukey-Kramer procedure. And you might, however, come across people doing something similar, not similar, it has the same function, in industry or other people that you speak to that study at different universities or different departments. They'll refer to something known as a Duncan ad hoc procedure or the Spearman procedure for groups. It really is the same. It has the same thing as Tukey-Kramer. But we're going to use Tukey-Kramer to tell us, say for example, and I'm going to use this example. Let's say there's 4 groups of students. I divide the class into 4 groups of students, and there's 4 groups of students, and I do an ANOVA to see how many hours they spend studying in a week, and I reject my null hypothesis. So let me use my pen for dramatic effect, excuse me. And I reject this null hypothesis, and I accept my alternate hypothesis to say that not all groups are the same. What I'm going to use Tukey-Kramer for is to find out, is this group not significantly different to that group? Or is this group significantly different to that group? Or is this group significantly different to that group? And then I'll continue by then starting with group 2 and saying, is this group significantly different to that group? Or is it significantly different to that group? And then finally, are these 2 groups significantly different or not? Okay, so that procedure, the Tukey-Kramer procedure, can be a form of hypothesis testing. I could state an hypothesis for each one of those comparisons that I want to perform. And so we're going to go about doing that. And the Tukey-Kramer procedure has got 4 basic steps. And let's start by looking at what those steps are. The first thing that we need to do is we need to establish the number of pairs. And we're going to use a formula, C. We remember C refers to the number of groups. So it's C times C minus 1 divided by 2. So in the case of that example that we looked at earlier on, where I had 4 groups, C would be 4. So it would be 4 times 4 minus 1, which is of course 3, divided by 2. And the answer of that would naturally be 12 divided by 2. So there would be 6 pairs. And then the next thing that I need to do is I need to calculate the absolute mean differences between all pairs of mean samples. And that contrast is the absolute mean difference between all pairs. So I'll have a look at the mean of group 1 and I'll subtract the mean of group 2 from that, and I will convert that into an absolute value. I'm always working with absolute values, and that's very important to remember. Step number 2 is I'll calculate a critical range for the Tukey-Kramer procedure using this equation. So in this equation, you will see everything here is familiar to us. The only thing that's not familiar to us is that constant value there. which we obtain from a table. That's the Q value. And the way that we read of the Q table is the degrees of freedom in my numerator that I use is C, which is my number of groups, and in my denominator is N minus C, which is the total number of observations minus the number of groups. I think the best way to try and explain this is to use an example. So if we look at the formula, we see MSW is in that formula, and we know that we obtained the MSW from our ANOVA one-factor F test. We've calculated that mean squares within. The critical value, getting the numerator is the number of groups, getting the denominator is the number of observations minus the number of groups. And so if we look at an example, we can try and do it ourselves. That example that we referred to earlier, when I said I divided the students into 4 groups, if there are 4 groups, then my C would be 4, and that's the value I use in my numerator. In this example here, as I put on this slide, you can see that the number of observations is 13. So in my denominator, I should use 13 minus 4, which is 9. And then I have to go and find the table. So the Q table will be given to you in your exam, like with all the other tables. And in my numerator, I should be looking for a value of 4. And in my denominator, I should be looking for a value of 9. So my Q value, or the value from the table that I will get, is 4.42. So I'm going to be substituting 4.42 into my Q value here in my formula. And let's see the other things that I need. Looking at my example, again, MSW was obtained from my one-factor F test. And now also need to know the number of observations in each of those groups. I need to calculate that critical value for each pair that I'm comparing to each other, for each of the hypotheses that I'm setting. So if I'm comparing group 1 to group 2, then I look at the number of observations in group 1 and I look at the number of observations in group 2. Now, if I have a nice simple example where the sizes of the groups are all the same, then that's nice and easy, because then I'll have the same critical value for each pairwise comparison. The problem is if I have an example like this, where I have 4 observations in group 1 and I have 4 observations in group 2, but I have 2 observations in group 3 and 3 observations in group 4. So when I compare group 1 to group 2, in my formula, that would be 4 and that would be 4. But when I compare group 1 to group 3, that would be 4 and that would be 2. When I compare group 1 to group 4, that would be 4 and that would be 3. And so you've got to do that for each pairwise comparison that you do, which is why I called it fun. You calculate a different critical value for each pair. And that takes us to step number 3, which is you compare each of the pair's means against the corresponding critical value. So you take the absolute contrast, which you calculated, and you compare it to the critical value, which you also calculated using the formula that we've just explained. And so you see, it's very useful to draw a little table like this so that you can have a look at pair 1 and pair 2. You write down the absolute value and then you write down the critical value, and then you can see if there's a significant difference or not. But that you'll only complete, that part of step 3 is really also part of step 4, which involves the decision rule. The decision rule for Tukey-Kramer is if the contrast, that absolute value, is greater than the calculated critical value, then you reject the null hypothesis. And the null hypothesis for each of those comparisons is that the pair is the same. And the alternate hypothesis is that the pair is not the same. So if you reject the null hypothesis, you accept the alternate hypothesis, and so you can declare if any pair is significantly different to the other. When we conclude, we don't have to conclude on each individual pair. We can basically, we use that table that we constructed for step 3, and we can say, you conclude as you would for a normal hypothesis test. You can say at 95 level of confidence, 95% level of confidence, there is enough statistical evidence to accept that pairs, and then you can say which pairs are the same, and then you can also say which pairs are different. So you can do that all in one go, but you need to, once again, to be able to do that conclusion, to be able to state that conclusion, you need to understand what it is that you are doing. Okay, so for now, guys, my beautiful, beautiful student, that's all I have to say. I will see you in class on Monday, and happy studying. Love you lots.